Hiya folks, hope you're all doing well. I thought I'd make a tiny little video series actually going through one of the past midterms that I posted up on OWL. I'll be going through the 2016 midterm, so if you haven't tried that one, give it a try before watching me go through my solutions or reading any of the solutions that I posted on OWL. The reason I'm doing this is, one, I've gotten positive feedback from making the occasional video in some other classes. I want to try it out with you guys. If there's good feedback, maybe I'll keep doing it. I might be able to squeeze in another one this week before the midterm. If there's not really any buzz about it, then okay, maybe I won't do anything, or maybe I'll make sure to do one for the next midterm if there is positive review. The other reason I want to do this, aside from, people just seem to like it, is because I want to sort of slow it down and explain the connections I'm making so that you can try and make the same connections. Doing well in any course, but especially something like 1501, where it's more about your theoretical knowledge, and if you understand the theory, you should be able to do the calculations fairly quickly. That sentence got away from me. What was I going to say? By the way, I don't edit these. Something about it's a theory-based course. It's very important to understand your way to think through a question, I guess, is probably what I was trying to go for there. And it's not so much about memorizing that, oh, last year they asked a mean value theorem question, so I better expect a mean value theorem question this year. No, if you know the mean value theorem, you'll be prepared for it, but you'll be prepared for any incarnation it can take. And so you shouldn't just look at these tests and say, yep, they've got one of these, one of these, one of these, that's all I need to study. It's about the connections you make, because, well, we can ask you some very weird, say, Rolle's theorem questions, and you got to be prepared to handle that. And it's not just about, well, I did last year's midterm, it's about how you think about Rolle's theorem and how you make these connections. Anyways, that's enough ranting and raving, as you know I'm prone to do in class. We're just going to start with question number 1 in this video, and then move on to question 2, and so on, and it'll make a nice little series here. So I'll try and write on the page. I do have a little booklet here in case I need to write some rough work, because you guys get some rough work on your tests as well, but we're just going to go through the questions we've got here. So problem number 1, prove that the limit as x approaches 2 of absolute value of x minus 5 equals 3. Use the epsilon delta definition of a limit. Now, we didn't, I think we might have done one slightly non-linear one in class, but we gave you guys sort of a worksheet that had a couple of these on there, and hopefully you've taken a look at them, especially if you're a little nervous about your epsilon delta definitions. So remember, the way these things work is, if I've got any epsilon, and it can be arbitrary, well, it's supposed to be arbitrary, we need a delta, so that if I tell you that I guarantee x minus 2 is less than delta, then that'll guarantee that this function, so yeah, you can't forget these absolute values, otherwise you've changed the question, but that this, the difference between this function and the 3 that we claim the limit is less than the epsilon. It's a little bit of a back and forth. Epsilon is sort of the error you might expect, and delta is, well, how close do I have to get to x to ensure that you get this small of an error, a difference between the function and the actual limit. Okay, so that's the challenge, and if we're doing this nice and neat, we need to say something like, well, here's my delta. Except I don't know what my delta should be. So I can, work backwards, I can play around. Eventually I'll come back, fill in this delta, okay? And then at the very end, the last sort of thing I would want to have is implies that x minus 5, the difference between the absolute value of x minus 5 minus 3 is less than epsilon. That's ultimately where we want to go with this. Okay, how do we get from there to there, and what delta should we pick? Sorry, how do we get from this statement here with whatever delta we pick? Okay. So this is the general layout. This is what we need to have. So we let epsilon be arbitrary. We would give someone a delta. We'll figure it out from rough work or some calculations. We start by assuming this statement. And then we want to just show a series of implications and wind up with this statement. Okay? That's what every epsilon delta proof looks like. The question is, how do we fill in this giant gap of white space? Okay. It's different for each question. If you've read some of the textbook, you'll know, for example, that with quadratics, you usually get this extra number c, and that helps work things out, and that's great. That works for just about anything, actually, getting a nice little c value. Now, absolute values, they sort of have their own approach as well. So the problem here is absolute values are tricky. Okay, absolute values, they break up nicely with multiplication and division, but I've got absolute values around absolute values and a subtraction. So what I don't want to see here, what I don't want anyone saying is, well, these absolute values don't really matter because we've got bigger ones out here, so we can just do something like this. Okay, you can't do that. You can't just get rid of absolute values unless you could somehow come along and guarantee me that x minus 5 was positive. Because if x minus 5 is positive, then yeah, the absolute values aren't adding anything. And that actually is sort of the underlying question you have to ask, is absolute value of x minus 5 is nothing you can manipulate and work with. But if I could guarantee something about the inside function, either that it's positive or it's negative, suddenly absolute value of x minus 5 doesn't need the absolute value bars. So here's what I mean. So you might remember from whichever Calc 1 you took that it's a piecewise function. So it means x minus 5 if you know x minus 5 is positive. And it means negative of x minus 5 if you know x minus 5 is negative. I guess technically there should be a less than or equal sign there. Okay? Now, to start manipulating our expressions, I really don't want these bars here. So what I'd like is to guarantee one of these two statements. And then I could say, well, x minus 5 in absolute value can just be equal to one of these expressions, because then I get rid of the absolute value bars here. And that's a great help. Okay, so how could we do this, and how do we think through it? Well, let's stop and remember, what do limits actually mean? Okay, the x values are getting really close to 2. The function, absolute value of x minus 5, they say it's getting really close to 3. But if our x's are really, really tiny, really, really close to 2, like 2.1 or 2.001 or 1.99999, can we make some sort of guaranteed statement that, say, x minus 5 is always positive or x minus 5 is less than 0? I'll put it to you another way. Let's graph x minus 5 in absolute value. Okay, over here at 5 is where it's going to be 0, and beyond that, it just makes the customary v. Now, where are we? We're at 2. Okay, so we're at 2, but around 2, the function doesn't just look like absolute value of x minus 5, it looks like this line. What line? Negative x plus 5. Which is the negative side of things. So around 2, if I get close enough to 2, absolute value of x minus 5 is just negative x plus 5. Okay, can we actually show that? Sure. Really, anything as long as we're closer to 2 than 5 is. So if we're within 3 of 2, okay, so if our delta were anything less than 3, we'd be all set. So, okay, well, it's customary to say something like, if delta is less than 1, usually, we really like delta less than 1. It's not guaranteed that you have to do that one. It's just customary if you're trying to do what other mathematicians do. So if delta is less than 1, x minus 2 being less than 1, because it's less than delta, so it's automatically less than 1, what we can do is we can just sort of split this up. And now we want to talk about x minus 5, so let's subtract 3 from both sides. X minus 5 is now guaranteed to be less than 0. In fact, this is true as long as you took delta less than 3, as I already remarked. But usually we say delta less than 1. Why? Just convention. Don't worry about that. Okay? So if part of my definition of delta includes the statement, includes sort of a guarantee that delta will be less than 1, I'll be able to ensure something like this, which tells me x minus 5 is guaranteed to look exactly like negative x plus 5. Okay? So if I can guarantee that absolute value of x minus 5 is negative x plus 5, suddenly this last statement just needs to be something like this, because these two are equal. Okay, now let's clean this up a little bit. That would be negative x plus 2. Okay. So there, to get between those two statements, we just sort of separated plus 2 into a plus 5 and a minus 3. Okay. Now, what could we have? Well, I'm going to take out a factor of 1 here, or of negative 1, and we'll get x minus 2 times negative 1 in absolute value. So I'll slow that down. I'll slow that down a little bit for you, in case you're uncomfortable with absolute values. Negative 1 times x minus 2. If I can guarantee this line, the next line follows just by multiplying in the negative 1. Okay. And we're going to continue to work backwards. How could I get this minus 1 in here? Well, if I just multiplied... In fact, I don't even need the brackets here anymore, do I? Okay. Because absolute value allows multiplication. It doesn't allow addition and subtraction so easily, but multiplying brings things in the brackets. And this absolute value of negative 1, well, that's just 1. Okay. So as long as I can show that x minus 2 in absolute value is less than epsilon, and that delta is less than 1, we're going to be all set. Okay. Okay. Now I've reached back to my previous work here. So what can we do here? I want to sort of write this up a little nicer, a little neater. But look at the connections we are at least trying to make here. Oops, put a pen there. We started by just talking a little, we got our basic setup. We've talked a little bit about delta. I haven't even said what delta should be yet. But by exploring, we have gotten rid of the pesky absolute value sign and turned it into a nice, easy-to-use linear expression. And as soon as we had that, suddenly a lot of things started happening in reverse. And it's okay to work backwards, as long as your implications work out just fine. Okay? So now, well, what can I do? I'm going to clean this up a little bit because I want to present this nice and neat for a TA. Okay? The rest of this was all exploring. So here's what I'm going to do. I need delta to be less than 1. Okay? Otherwise, I can't get the rest of those calculations. And I will have to write that up again. But I'm going to let delta be the minimum of 1, and, well, we'll need something else, and we'll use that in just a moment. Okay? So we've got two sorts of things going on here. So x minus 2 less than delta, well, that'll be x minus 2 is less than 1, because delta being the minimum of 1 in something will always be less than 1, or less than or equal to 1. And so then we had this. We subtracted 3 from both sides. And so we were able to guarantee that absolute value of x minus 5 is negative x plus 5. And I might call this relationship star. Where did we use star? Well, we used it further down the page to go between these two. Okay. Now, the question is, how do I get from here to here? Well, this absolute value of x minus 2 looks awfully similar to this absolute value of x minus 2. In fact, let's work one step further back. We don't even need this 1 here anymore. So as long as I can go from delta, x minus 2 in absolute value is less than delta, to guaranteeing that x minus 2 in absolute value is less than epsilon, I'll be all set. Well, how could I do that? Well, if delta was always less than or equal to epsilon, we'd be all set. So we just let delta be the minimum of 1 and epsilon. Minimum of 1 means all this stuff over here works, and we finally get our last statement star that we need later on. And delta being less than epsilon guarantees this chain of events, which allows all our work down here, and all these implications go forward. Absolute value of x minus 2 being less than delta ensures that absolute value of x minus 2 is less than epsilon. Multiply a 1 on one side, doesn't change a thing. Change that 1 into the absolute value of negative 1. Again, you haven't changed anything. Bring the negative 1 in. All of these are equal. Everything is equal up until that last statement, and star tells us that these final two statements here are equal, or are equivalent. Okay? We needed to show star, otherwise we couldn't do this last line, and that was the crucial line that had the all-important f of x minus L less than epsilon. The function minus, the difference between the function and the limit is as small as we want. Okay, that's how we got that final statement. So absolute values, can be a little pesky, but to do an absolute value question, what you need to do is just be able to ensure that we're close enough to 2, or we're close enough to 5, or we're close enough to 20, or whatever it is, that I know what the absolute value function looks like. Instead of just saying, well, absolute value bars is, I guarantee you that it looks like this line or this line. Because linear terms, as we saw in class, are a lot easier to work with. Okay? So that's me going through, working the question out on my own. I'll see you guys in the next video for question number 2, and we'll talk about how we should think through that one as well.